CNC router milling offers lots of opportunities to make fantastic things in a very controlled manner, but there are some limits to what can be done. For a 3-axis router, such as the one in school, the most obvious limitation is that the CNC can only move horizontally in the X and Y axes, while sequentially adjusting the cutting height with the Z axis. The rotation of the router bit is always perpendicular to the XY plane, so even though you can make things in 3D, in effect it will always be a sort of 2.5D relief with variable height. As deep as the router bit cuts for a certain position, all material above that given position will also be cut away in a subtractive way, layer per layer. With a 3D printer, which works in an additive way, layer per layer, you can have layers which bulge outwards and inwards and out again in a true 3D fashion. With a 3-axis CNC router, no material can exist vertically above any cut material, due to it being necessarily subtracted by the perpendicular nature of the router bits. Overhangs are impossible to fabricate. Another limitation is that for any router bit used, there is a maximum possible cutting depth defined by the vertical distance from the bottom edge of the router bit to the lowest part of the collet holder, including a significant safety margin. This is not the same as the total length of the bit, since the bit needs to be firmly attached in the collet, inserted into the collet a distance of not more than 2/3 of the collet depth, around here. It is absolutely imperative that the bit is not inserted further into the collet than 2/3, since the construction of the collet, as one can see here, relies on fixating the bit by squeezing it tight enough for it not to be able to move vertically. But if it is inserted too far, there is not enough squeeze room to hinder the bit to travel upwards, and if this happens, the machine's rotating spindle might interlock and break down, like it did last fall. Additionally, one has to make sure that the operation instructed to the CNC is safe to execute without any collision between collet and material, by simulating and taking into account the thickness of the material and the total depth of the cut. The CNC router is a very powerful machine, but it is not perceptually aware of its surroundings, and does only know the XYZ coordinates it is traversing. If given inadequate instructions, it cannot by itself avoid disaster. Therefore, you must be present at all times during the operation of the CNC router, and take great care in preparing the operation in the Fusion 360 software. This includes making sure that the total cutting depth is significantly less than the maximum cutting depth of the router bits, so as to make sure that the collet holder never collides with the material you are cutting. This touches upon a third limitation. Any given router bit has a cutting diameter, often but not always the same as its shank diameter, and due to the simple fact that thicker bits are more rigid, they can be made longer, and thinner bits are most often much shorter than their wider counterparts, so as to maintain rigidity and not too easily break. This inverse relationship means that you will have to balance precision against total cutting depth. If you want to cut deep, you will probably need to use a bit that is both long and wide, which will sacrifice comparatively more detail, as opposed to a smaller bit, which can cut more precise, but cannot cut deeper than its comparatively shorter extension. A fourth limitation is directly related to the third, and that is that the choice of router bit diameter not only probably affects the maximum cutting depth due to the length of the bit, but also definitely affects the magnitude of the radius left uncut at concave corners. Since the router bit is cylindrical in its cut, it cannot cut inside corners straight, or pockets smaller than the diameter at all. Instead, there will be some material left, equal to what the radius of the router cannot reach. This is not a problem for convex corners, like this one here, since the router bit can freely move around the corner. But for concave corners, the radial remnant is a limitation of cylindrical routing. A smaller diameter router will diminish the problem, since it will reach farther into the corner due to it having a smaller radius. But that comes at the cost of a longer time to mill the material, as well as other limitation considerations a change of diameter entails. One may also author the model to be milled so that concave corners are inset by a small distance, and therefore eliminating the residual material at the cost of subtracting more than originally intended. But for this introduction, this is not demonstrated. A fifth limitation, already touched upon, is that milling operations take time, and if you refuse to sacrifice detail, you might be shocked at how long an operation might take. The time it takes depends on quite a few parameters, but in essence, all influence how long a distance the CNC router is instructed to cover. If you decrease the height of each pass, the pass depth that is, and thus reduce vertical stepping and vertical banding, the time required will increase. If you choose a router bit with a smaller diameter, the CNC will have to traverse a longer distance, since it will have to backtrack to cut what a wider bit might have taken in one go. Additionally, if you decrease the feed rate, the speed at which the CNC router moves through the material, to accommodate cutting in a relatively harder material, the distance traveled might be the same, but it naturally will take longer to cover. Before going forward to the software workflow, let's recap the limitations. For 3-axis CNC routers, only 2.5D-like geometry without overhangs is possible to fabricate. There is always a maximum possible cutting depth, depending on the length of the bit used. You will have to weigh precision against cutting depth when choosing the diameter of the bit, probably. For concave corners, there will always be residual material, the magnitude of which is depending on the diameter of the bit. CNC milling takes time, and bearing in mind that you need to supervise the operation at all times, you can only go without lunch or bathroom break or sleep for so many hours, so you will need to balance your fabrication ambitions with the time milling actually takes, and plan ahead. The whole process will take longer than just the actual milling, and in nearly all cases, the milling takes longer than you would expect from the simulation. With all of these limitations in mind, let's make some millable geometry. For simplicity's sake, and also to make sure that the milling does not take too long for demonstration purposes, we'll take this image, which unprocessed already looks like something of a height map, which will be fitting to extract 2.5D geometry from. We want to state already here that any geometry which adheres to the previously stated limitations can be milled successfully. And this is just an example for the purpose of the demonstration of the Fusion 360 CAM software. Let's double-click to have the top viewport in full screen and enter the command picture. And we'll choose the freshly downloaded file. We'll press 0 to have the first corner in the origin point, and the next one can be anywhere because we haven't assigned a scale yet, but we will now. As is already observed, the grid of the machine-learned model is not rectilinear, not as a rule at least, but we'll take one dimension. So we'll make a scale command and take this here, this dimension, and have that as a reference, and it's 5 meters, so 5,000 millimeters. We'll zoom select with CS and enter. We can press M to move, and we can move the corner to the origin, and then we can zoom select again. This is in scale 1 to 1, and if we now scale it to from the origin point, so 0 here, and the scale factor should be 1 divided by 100. This is a non-assignment scale, but it is suitable time-wise for the demonstration purposes of the actual milling, so 1/100th there, and ZS to zoom select. And now we have a reference picture here in the correct scale that we want for this particular purpose of demonstration. Now we can enter the command height field and we can pick the same. And of course, if presumably you will process your, or you will like find your way of creating this model and translating the image into 3D. But this is just for demonstrative purposes, of course. And then it's then we use the unprocessed image as this. And the first corner can be the origin point, so 0. And the second corner should be this corner of the image. And now we can define the parameters of the height field. And we found that 200 times 200 with the interpolate surface through samples method works fine. And regarding the height, this is important, like we talked about with the limitations. It is important to know that, or to remember that the height of the milled geometry cannot be higher than the maximum allowed cutting depth, including a safety margin, so as to reduce the risk of colliding between the material and the collet. And to determine a suitable maximum height, one may do something like this. We have inherited a tool library from Gabriel, and Gabriel, since he was a MultiCam master, he had a tool library in MultiCam, and we are not proficient at MultiCam, but we downloaded the demo version, and the demo version comes with a tool manager, and thus we can just check his tool library. And we will try to, in as close of a future time as possible, migrate this to a Fusion 360 library, which should be straightforward, although requires some manual input, of course. This tool library might not be totally accurate in relation to those bits, those router bits which are actually available in the shop, in the workshop. So we will make sure that it's accurate as well. It will be fun. Here we will use the 16mm flat end mill due to its both that it's wide, 16mm is wide, and that means that it's effective. It can mill much material in, I will say, one go, but I mean comparatively shorter toolpath than if you would use 6mm as an example. So we take the total length of the bit, which is 97mm. So 97, and we subtract the 3 centimeters, 30mm, which corresponds to about 2/3 of the collets, which the bit should be inserted into the collet, about 2/3, not more than 2/3 of the collet's depth. And then we subtract another centimeter, another 10mm, as a safety margin, so as to increase the distance, the possible distance between the material and the collet by a whole centimeter. That is a fair safety margin, so to reduce the risk of collision between material and collets. Okay, 57mm is 1mm shorter than the stated cutting depth of the router bit, which means that if we restrict the depth of the milling to a maximum of 57mm, not only do we reduce the risk of collision, but we also make sure that the material is only in contact with the sharp flutes of the router bit and not the smooth shank. As long as the shank is not wider than the diameter of the cut of the flutes, it is okay to cut deeper than the cutting depth, as long as a reasonable margin is maintained, since the cut would make sure that there is no friction between material and shank. But if the shank is wider than the cutting diameter, like this one, then it is imperative not to cut deeper than the length of the bit which is equally wide as the cutting diameter, because otherwise you will seriously risk collisions between the wider shank and the material. Alright, so 57 was what we arrived at. Alright, we can press OK. We don't need to save this because we have done it before, but preferably you will save. With its placed, we can change the perspective, and we can press ZS to zoom select, and then we see here, we can change from wireframe to shaded. We can see here that we have the height field, and it corresponds with the reference picture here. But we'll need to fix two things for demonstrative purposes. And the first is that the height field is created with white situated at the chosen maximum height, 57mm, and black at the original plane height. For this image, since the color range does not extend from black to white, but is mostly light, or mostly light colors, or light grayscale values, we can scale 1D. So let's do that. So scale 1D, and that should be more suitable in the front space. Zoom select yes, because then we can scale 1D and pick a point which appears to be furthest up. Yeah. And then we can, by pressing tab, we can lock the direction, and then simply by zooming in here and making sure that it's about correct there. Now we have that positioned correctly, and since we already have the reference picture, we can use that that outline here, or that end point, as the final destination. So now we have normalized it or scaled it so that it covers from 0 to 57 millimeters, but we find that it's inverse, or it's upside down. So let's mirror it as well. And mirror we can do with the mirror command, and then we can do with the 3 points. So we just click there or press P, and then we can define a rectangle here in the XY plane, and we can with Control H hide the original, and here we have it. But now it is, since it was mirrored and its top was in the origin here, or in the origin plane, we can M to move, V to vertical, take one of these points, which presumably are the lowest, or situated in the lowest plane, and we can press 0 so that it is moved vertically to the origin plane, or the XY plane. All right, we can make a bounding box of it and confirm, and then we can just see here that it's 57 millimeters in Z axis in height. So that's perfect. All right, we can either delete that or simply undo the command. Yes, I think I've missed a step in the preparations, but we can redo it here anyway. So if I press Control Y to redo that, and it was stated there. I do remember that it was 57 point something. So it's 57.098. Now we should make sure that I'll just temporarily undo that this height field is just a plane, or it's not a plane, but it's a surface. It's a surface. Actually it is a 2.5D plane, because it's a subdivided plane with the Z values adjusted to the height map, or the height field. But we will make sure to make this a closed polysurface model. Since we will be milling with a material which has a thickness of 69 millimeters, we will make sure that the highest point of the mill geometry is at the top of the material to be milled, and that the bottom plane here is situated so that the rest of the material serves as a platform, or serves as a floor for it. And we do this so as to reduce the amount of milling, because milling takes time. If we would have this in the bottom here, or like only a couple of millimeters, or say half a centimeter up, then it will take more time to mill above it. But if we position it so that it's at the top surface of the so-called stock material, the material to be milled, then it's more efficient in terms of time. So yes, and this was 57, that we don't need to change. So well, okay, and then we can just take 69 millimeters, which is the thickness of the material. 69 millimeters subtracted by 57 millimeters, which is the total height, or approximately the total height of the model to be milled. And we see that since the difference is 12, we move this up 12 millimeters. Move vertically, pick any point 12. And now we can make a box, origin point or first corner origin point, second corner other part or other corner on the diagonal here. And then it actually doesn't matter how high as long as you make sure to include that. All right, I'll switch now to ghosted mode so as to see here. And then we can scale in X and Y so that it is fitting our expectations. We can actually make this a little smaller so as to save a little more time during the milling than previously prepared. Yes, something like this could be interesting as well. It's just for demonstrative purposes, so it's good. Okay, we can temporarily, or we can deselect that, and then we can do Boolean to objects. And then we can take this box and this surface, and then it's automatically booleans a preview, and we can see that this is not the one, so we click once more, and we see that this is not the one we want, and we click once more, and we see that, oh, this is the one we want. And we press space or enter to confirm. All right, so here we have our closed solid polysurface. We can change to shaded, or we can actually change to Arctic now just to see that this is like this is the original, or it's not the original, but this is like the art of CNC is one of not rationalizing, but there will always be a translation where detail is lost, but to what extent you decide, depending on how much time you want to assign to the CNC operation and the diameter of the bit that you want to use and the scale of the mill geometry as well. This looks fair enough for demonstrative purposes. All right, I'll change back to shaded. Then we can make sure that this is situated in the origin or aligned to the origin by one of its corners, and more precisely it should be, if we temporarily hide this, you can see that the green one is Y and the X, and the red one is X, and it should be situated so that its lowermost, forwardmost, leftmost corner is in the origin point. So M to move and 0 to move its origin point. With such a straightforward outset, the process is equally straightforward. So now here we have it. So we'll press File and Export selected. And now here it's very important that you export to Rhino 5, because Fusion 360 has different licenses, and they are trying quite hard to make sure that you demo model, that you are not satisfied with the educational license or the... I don't know if I'm talking in my nightgown here, because perhaps it's the hobbyist license which is limited. But anyway, we will be using an educational license, and it will work. But make sure to save it in a Rhino 5 model file. I will save it as with a suffix here. Yeah, we're already at Fusion. Yeah, this is really unprofessional, but I couldn't manage to get the screen recording software to work on the laptop here. But if you don't have Fusion 360 installed already, then create a student account on Autodesk, which perhaps you might have for other reasons, because they are responsible for a lot of software, including AutoCAD. Yes, but when you have it, you just press already have educational access, sign in, and you're signed in, and then if you search for your platform, your operating system, you find the product that you search for, which is Fusion 360. And then you press get product and it's install, and it's downloads the installation file. I started here and logged in. But here you can click new projects, and then you create a new, it's interesting that it's called a new project because it's more like a new folder for individual, I would say individual projects, but it can be individual, it is individual models anyway. So here I've already created a new project called demo model. If I double click that, we find all models in the demo model project. And since for consistency's sake, since we made a new in the tutorial here, I'll click select files here, and then we can choose this one instead, and make sure to upload. And it might take a time because it also converts the file, so it's not just pure uploading. And it might feel, yeah, but now it's complete. Okay, and then you can close. And here you see that there's a new model here, which if you double click on, it will load. When you import a model, you can see that the direction of the axes are correctly aligned. Here we have the model, and the first thing that we should do is switch workspace from design to manufacture. And in this workspace, we can click setups here, or actually we can right click and click new setup. And this is the stock setup set for this. And it's a good thing to remember here that your actual stock material might, and for this demonstration, will be larger than this stock here, than this light beige yellow stock previewed here. It will be larger than that. But the most important thing to know about the stock here is that the stock defines what Fusion 360 will excavate, so to say, will with subtraction compute operations to excavate the model underneath, so to say. And this is important because if, like we have a lowest point platform which begins here 57 millimeters below the surface, so to say. And although with the routing bit that we use, it certainly could cut deeper, but we want to make sure that it actually does not. If you define the stock here to extend beyond the actual model, then Fusion 360 will excavate the model also below here. But if you make sure that, I can just step by step here, in this first setup tab, setup, it's actually, nothing needs to be changed right now. We will change the origin point when we have redefined the stock extension. It can be done now as well. But now when we change the stock here in the stock tab, and with the relative size, like its default, and Fusion 360 is really user-friendly because most settings, if you hover around long enough, then you get these really helpful tooltips here, so as to make sure that the toolpath does not extend beyond this floor. We'll make sure that the stock side offset is 0. So I'll input 0 here, and I'll actually input 0 here, like that, and we saw that it shrunk. The stock top offset, it might be a mistake on my part. I'll try to open the file here, but let's see here. The workbench, tutorials, introduction, Rhino, demo model here. I will just check here if I do a bounding box here. Yeah, it says 69 millimeters, which makes me... Yeah, I can actually see now where the problem is. You can see here that, I don't know if I can zoom in on this. Yeah, here we have the problem. The automatic stock generation did not find this geometry to be worthy of including. So we'll simply, well, it's quite good because that means that it's not that much of an issue. Okay, here we were. And what was found that in the manufacturer workspace, when we added a new setup, when we were in the stock here, we can see that the height here is less than we expected from the bounding box in Rhino. It should be 69. But that is simply because this stock top offset, or the reason is because it didn't include this top here. So we'll just add a stock top offset until it is included. So there we have 69 millimeters, around 69 millimeters. So with a stock top offset of 8 millimeters, so as to make sure that this part is actually defined in the milling, or actually represented in the milling of the stock material, and with a 0 stock side offset, so as to make sure that this outer edge is not milled. All right, let's see now. And I can just say that already now that then when the CNC router has milled everything here with utmost precision of the computer numerically controlled operation, then we can just make these 4 slices we can make with the hot string in the assembly workshop. All right, but now this matches up, and I see that I have done a mistake there, but that mistake is it's a mistake simply in my preparations, because I had prepared with like a faucet, so that I know that I'm not teaching you an incorrect method in regards to the setup and setup of the stock here. But I found that my screenshots were by human error corrupted. All right. So then it's really important that you make sure that the origin point is situated at this point here. And with this highlighted, I think it's just to click there, and it is. So this is the top point above the origin point. That is important. Or actually, what is more correct is to state that if this y-axis and this x-axis, if this is the most forward, most left, leftermost, forwardmost corner, then it's the stock corner. Because if you offset these sides, if you have such a reason for any other, like say 15 millimeters here, then it is still this that should be your designated origin point to communicate with the CNC router. But for now we choose 0 so as to make sure that this is not milled. All right, so that's how easy the setup is there. So we'll press OK. And with a setup made, you can add, with a setup made, you can add a 3D adaptive clearing toolpath here. And that you will have to select a tool and Actually, it says here it's the 12mm one. Yeah, which is great. I was just not expecting that, but that is actually great. So it's a 12mm in diameter. I know that I thus erroneously showcased the 16mm in the tool library, but that is a good mistake to uncover now, because it's the diameter of the router bit. It defines very much, as was previously discussed or previously presented with the limitations. When preparing for this, we used this and this end mill, and it turned out very, very adequate in terms of time to mill as well as precision. So it's very good that it was this, and we will make sure to make available this tool library, and of course we will expand it so that it's more reflecting upon what end mills are actually there. All right, I will select that. But it's that one goes without saying, but of course in an introduction it should really be said that the tool you select here, and it can be in a tool library like it was, and when you have selected it for a toolpath in a project or in a model, then that is also, it's duplicated as an instance for your actual, I think as a copy though. Yes, but it's very important that these parameters are correct in terms of the actual bit that you will insert into the collet and use in the actual routing at that particular tool number. Right now, as you see here, number, and also here, the number that is prefixed here. That is a tool number, and for this introduction we will only use one tool, and in such a case it is the only thing that's very important is that the tool number is the same assigned here in Fusion as it is placed in the actual tool holder in the at a CNC router. But that will be made obvious during the introduction of the actual CNC machine. All right, but as we had it selected. And here there are lots of interesting settings, and this is about feed rate, and speed. And feed rate is about how fast the router, the actual end mill or the CNC machine, actually how fast it moves the end mill through the model and through the layers. Through each layer, how fast it moves horizontally. That is the cutting feed rate here. And the cutting feed rate has a relationship with the spindle speed, and the spindle speed is how fast the end mill is rotated around its axis. And the main thing to bear in mind here is that different feed rates requires different spindle speeds, different RPMs here, to maintain a sustainable feed per tooth. The tool here, the end tool I say here, but the end mill, it has 1, 2, or 3, or 4. It has a particular number of flutes, and each flute is very sharp, and each flute will, in its revolution, take away some of the material. And since this end mill is defined, we can check that here as well. It has, how many flutes does it have? It has 2 flutes. So for each revolution, which it does 5,000 times per minute, it will have 2 flutes removing material from the stock material. So if we increase the feed rate from 1,000 millimeters per minute to 2,000, we can see that the feed per tooth increases because the spindle speed is the same. But if we double this as well to 10,000, we can see that the feed per tooth is the same. So now the relationship between cutting feed rate and spindle speed is maintained because each tooth gets fed 0.1 millimeter of material in the toolpath. But the whole toolpath is, or the CNC router is moving in the material at twice the speed here. And actually, we have experimented with styrofoam, and we have found that 3,750 do not accept such a high that is said here, but if we make sure that is 3,750 millimeters per minute with an RPM with a speed of about 8,000, that yields a feed per tooth of 0.23, about 0.23 millimeters per tooth for this tool with 2 flutes. And we have found that yields adequate results. One important thing to note here is that when actually operating the CNC machine, the spindle speed can be increased and decreased as you like, but of course not arbitrarily, because you should always listen to the machine and feel like you will develop an ear for this, but you should be feeling how the machine sounds when it works, or like when it moves through the material, and depending on how the material is subtracted, because it should be for wood, it should be chips and not sawdust. So if you're getting sawdust, then you are having too high of a spindle speed, and you should decrease the spindle speed so that the feed per tooth increases, so that you get more like chips instead of wood chips, instead of sawdust. But that's a whole science, and we would love to, in dialogue with you, experiment and like make a map of suitable spindle speeds and suitable feed rates for different materials. And we have already initiated such a project, but it has been on ice for for a couple of years while we haven't been in school, and now we would like to revive such a project. All right, but those two, Fusion 360 is really user-friendly in terms of trying to help you set the automatic value. So when we changed the spindle speed, the ramp spindle speed is equally set as well. It changed that automatically, as well as the lead-in feed rate and the lead-out feed rate and the ramp and plunge. So you might not know what all this means, but if you hold, is it there? Yeah, if you hold on the actual value for a certain amount of time, then a tooltip will enlighten you what it actually means. So there's a lot to be learned, and we'd like to discuss it with you as well. For this introduction, we'll be satisfied with the basics of the spindle speed and the feed rates and their relation to the feed per tooth. it's perfectly adequate for this. All right, so these values are good for. I think that I was lost in when I was saying something important here about that when actually operating the CNC machine. The spindle speed can be changed, both increased and decreased, but the cutting feed rate can only be decreased, while the spindle speed will be used, of course, as the default value when the operation is run. It can be increased and decreased, and it will be stated as an RPM value, which you can increase and decrease. But the cutting feed rate, that will be the 100% of actual movement speed through the material, which is possible for that particular run of the operation that you have created an instruction for. So it is important to note that you can decrease the percentage from 100% to 80% or 50% if you find that the router is moving too fast through the material. But you cannot increase it. So it can be a tactic, but you have to be well aware of that you're using such a tactic, and like remember that very well when you begin. You can choose you can choose here a higher initial feed rate, even though if you know that the optimum is about 3750, you can choose, I will just write here 4250. And that will make 4250 millimeters per minute be the default 100% feed rates, which you then, as soon as the operation starts, can decrease to like I'm not very good at the mathematics side of this, but how much of a percentage 3750 is of 4250, I do not know. But you can like decrease it initially from the start to 70% or 80%, and then if you want to find a sweet spot, you can like slowly increase, and you can listen to the machine and how it sounds in the how it sounds when going through the material. But here I will, for this demonstration, I will have 3750. Very good. All right. When it comes to geometry, you don't need to change any default settings. For the demonstration, we'll move forward to the height here. And these are the clearance heights, the retraction heights, the top height, etc. And these can very well be left at their default values. The retraction height is here is defined at 10 millimeters, which means that when a toolpath has been completed and it moves from one place to another, it will retract 10 millimeters above the stock top, which is defined here as with a 5 millimeter offset. So these are safety margins which reasonably can be left at their default values. All right, now here's something important and interesting, because here at passes, you can see here that with a tolerance of 0.1 millimeter, that's the tolerance of curves, because each G code, which is the language that the CNC router speaks, and which is the language which you actually, with the help of a post-processor, actually generates, so that you can instruct the CNC router to do what you want. G code is actually just I think for the preparation that we made, it turned out to be 180 lines of coordinates in essence. And these coordinates are linearly defined, so it will move linearly from one point to another. And the G code, since it talks only in, or not only, but primarily in coordinates, and the movement between these coordinates, in effect, it will be a series of linear instructions. So the tolerance defines, as you can see here, how close to the original curve or the original curve geometry that the machine should be instructed to go. With a tighter tolerance, a smaller tolerance, there will be more lines of code, of course, which might not be, it might take longer, or it might not take that much longer, because it moves so smooth and so, yeah, you will see it's quite wonderful. Yes, this is the one, because this is the maximum roughing step down. The 3D adaptive clearing, that toolpath operation is it's quite impressive in terms of that it maintains always processing the materials, always cutting off material, but it makes it in a way so that it takes the least time, being the most effective, and also being most friendly for the durability of the router bit. And the maximum roughing step down, it is how deep into the material each pass is at the maximum. With the adaptive clearing, the router bit is instructed to first plunge this amount of millimeters down into the material, and then the fine step down, it goes up again in increments of this value. So here it's very easy that it goes down 10 millimeters into the material and removes the bulk of the material in that segment, in that 10 millimeter segment, vertical segment. But then it makes sure to excavate all the fine steps in steps of 1 millimeter. But since this is styrofoam, a very soft material, you can increase this, and also because you're using a tool which has a cutting depth allowing for this, you can increase this to 18 millimeters. But then, as you can see here, due to it trying to be Fusion 360 trying to be user friendly, it automatically changed the fine step down to 1.8, which will reduce the time the operation takes, but you will also lose precision, because the vertical resolution of the steps are nearly doubled. So you can revert this to 1 millimeter again. This way you will have 18 millimeters per roughing step down, and then it will be going and fine milling in segments of 1 millimeter. Yeah, and you don't want any stock to leave here. As was said here, stock to leave is the amount of stock left for subsequent roughing or finishing operation. And it's very good if you are doing this like this adaptive clearing as a first step, and then in the second step you could do it a spherical, or not spherical of course, but a round ball end mill to really smoothen things out. Then you could have this stock to leave and keep 0.5 millimeter of material of each of the geometry, so that the last finishing pass can define the final surface. But for this operation and demonstration, we don't need it. And here, when it comes to linking, I think that it's very fine. Yeah, here there's one thing. The no engagement feed rate, that is the movement speed of the router when it is not cutting in the material. So when it has retracted and when it moves to another point, it's automatically set at the same as the cutting feed rate, but it can be set higher, so we can set it to 5,000. Oh, let's see now, not 50,000, but 5,000. It's really important that you that you get these correct, so that there's not a stray zero, which you, like me, happen to insert there. And then when it comes to the ramp type, the helix is quite an advanced one, but you can change it to plunge. And the reason for that is because it allows more of the geometry to be milled or excavated, because helix requires a larger hole. So then you can press OK. And I think that it's computing now. I would guess so. Yes, it's computing. So when you have done that, it will compute the, and you can see it here. It will compute the toolpath. It will compute the toolpath. And it can take quite long, and it can take less. And all the yellow, that's the no engagement travel. And all the blue, that's the engagement, that's the cutting. And all the green, that's the lead in, where it smooths into the cut. All right, and now the toolpath is ready, but we will need to simulate it to see what it actually does. So we'll press here under Actions and Simulate. And we'll begin, and it begins here with the stock. And you can define different modes and colorizations and materials here, but we'll just have it. But I like to choose the tool. And then we can start simulation down here. And then you can see, and while we look at the simulation, we can also look at the statistics here. And it says that the machining time is 17 minutes with the settings we have chosen. And 17 minutes as a simulation estimation, it's perfectly fine. In most cases, if not all, the actual machining time is longer than the stated machining time, because the stated machining time here is like the theoretical run. And in the practical run, there will be some, the retractions might take longer, and the like. But here you can see how the adaptive clearing works, that it first takes away much of the material where much is to be removed, and then it keeps areas which should be more precisely defined or excavated, and takes those. And I'm about to collapse from sleep, so I'll just increase the speed here. You can do it down here. So I'll increase the speed. But here I want to slow down the speed because I want to make sure that it does not extend further than the further down. No, perfect. Yeah, so when you simulate, just make sure that the end mill does not go further down than you'd expect. You can click here to show the toolpath. It might not be so clear at all times, but you can check there. But always make sure to look at the simulation so that you notice anything weird and anything unexpected. When you're in the simulation, you can right click on the stock here, go down to stock, and then you can save stock. And you can save the stock here. And then you can open Rhino. And I just fetch from the zoo. And I can import the stock here. Yes, with default import settings. Open perspective. Zoom select, sorry. And let's go to Arctic. And here we can see this is like the closest preview you can get of the actual result, because this is how Fusion 360 will excavate your material, your stock, so as to excavate it as close as possible given the diameter of the end mill to the model. Yes, now you can go back to Fusion. And since we have simulated here, we can close the simulation and confident that this works as we intend, and also that it only took 17 minutes, so perhaps no more than 20-25 minutes, which is fair for demonstration, because then we can talk a little about perhaps Fusion 360 or how do you adjust the speed, that is the RPM, and the feed rate. But now you press post process under actions. And we will supply this. It's made by Jose. We don't know Jose personally, but this was supplied to us by Vasily, and it has worked and will work. The document unit is millimeters, but you can always make sure that it is millimeters. Yes, but then you can click post, and the name you can either change as the default name in the previous menu, or here you can simply type demo model and save it. And this nc.nc, that's a file extension for G-code. I can show you the actual G-code is just text, which the CNC router knows how to read because it's prefixed in the correct way. It's here. Demo model.nc. There. So here we can see that it's just text, but it's prefixed with these M90 and G0 and another. This was only like 94,700 lines of code, presumably because we changed the adaptive clearance maximum pass step. Alright, and this file, this gcode.nc file, that file you will need to either transfer or copy, preferably, copy to a USB memory and bring to school, or you can upload it to UG, to the KTH server, and if you upload it here, simply by dragging it in, then you can access it in school from the computer by the CNC, which has the connection to the CNC. I don't know if I have forgot something or anything or most things now, but this will do as a primer, not a primer, because a primer should be concise, and this was not concise. I think it's better if I go to sleep now and we can talk in the morning.